Okay, so one more issue with or one more sector that requires some net zero considerations and pathways is, of course, construction, which includes cement and steel. I'm going to give a brief intro to this issue of net zero for cement and steel with the Nature opinion piece that just appeared literally now on 24th March. Steel coils in a plant in Duisburg, Germany, produced using methods with low carbon dioxide intensity. So both for cement and steel, there is mining involved, either for limestone or iron ore. Obviously, there's transportation involved. There's lots of energy use involved for creating the clinker, the melting of the ores, and so on. So energy, emissions from mining, transportation, production process, inefficiencies in the system, not being up to date on the equipment, and so on, are all considerations. This report starts by pointing out that production of cement creates 2.3 billion tons of carbon dioxide per year, and making iron and steel releases some 2.6 billion tons. They are respectively 6.5 and 7% of the global CO2 emissions. So obviously rich targets in terms of thinking of net zero and drawdown. So the suggestions given include a few things like use the latest technologies. Improving insulation, for example, of industrial plants can save 26% of the energy used. Better boilers cut energy needs by up to 10%, and use of heat exchangers can decrease the power demands of the refining process by 25%. So there are many points made. I'm just picking some highlights, and you can see that there are identified places where significant reductions in energy and hence emissions can be made. Use less of these things. So small but significant changes to building codes and education for architects, engineers, and contractors could reduce demand for cement by up to 26%. And for steel by 24%, according to the International Energy Agency. IEA puts out some very nice reports, very detailed with data. I've recorded many podcasts based on their report, so this is a good report to follow up if you want. Reinvent steel production. Better, so there are some context given before. Better still, using only hydrogen for direct reduction of iron should reduce CO2 emissions to 50 kilograms or less per ton of steel, a 97% reduction. That is massive. Firms in Europe, China, and Australia are piloting such plants, with several slated to open in 2025 and 2026. The challenge, of course, is that this process requires a lot of hydrogen. How to get around it? One promising alternative to hydrogen is using electricity to reduce iron ore through electrolysis. This method is being explored by Boston Metal in Massachusetts and Luxembourg-based ArcelorMittal. Mittal is, of course, an Indian steel magnate. Reinvent cement. About 60% of the emissions from a top quality plant come from the calcination reaction, and most of the rest from burnt fuel. In total, the process produces about 800 kilograms of CO2 per ton of cement in an average plant, and 600 kilograms in a best-in-class plant. There are lots of other points about cement as well, using, instead of limestone, using some magnesium-based material, which reduces emissions. In Portland cement, for example, there are ways to mix ash, which we'll look at in a minute, and so on. So elsewhere I have podcasts on reducing emissions from carbon and steel as well. The other point, swap fuels. For cement, however, municipal solid waste or carefully sorted rubbish can be used as an alternative fuel. High temperatures in the kiln incinerate toxic materials in the waste, and the ashes can be incorporated into the clinker during the cement production process, going from limestone, coke to clinker and so on. There are steps involved which I'm being a little facetious about, so you can read up more. Capture carbon always works if it is scalable. One major issue is that the stream of CO2 needs to be more than 99.9% pure to reduce costs of compressing and storing the gas. Typical steel and cement plant fuels consist of about 30% CO2, the rest is mainly nitrogen and steam, so efficiency of CCS is going to be low, which means you have to be careful about the energy used for compressing and storing the gas as opposed to the actual amount of CO2 that is taken out of the system. Building heavy industries in clusters would allow heat, materials and infrastructure for making and storing hydrogen, as well as collecting and disposing of waste CO2 to be shared. So this is kind of a planning stage approach to towards net zero. Such clusters are being developed at Kalundborg, Denmark, Tyneside, UK, Rotterdam, the Netherlands, and Bergen, Norway. Progressive countries thinking about these things, and good that they are doing it, and probably will produce some data to see how much can be saved with this approach. Store CO2 in concrete. Turns out that cement and concrete both absorb CO2 from the air by converting calcium-based components back into limestone. The potential there is huge. In theory, roughly half of the processed CO2 emissions from cement manufacturing could be reabsorbed. Half of it can be reabsorbed. That's pretty stunning, right? But the materials would have to be ground up at the end of their lives to make the concrete particles smaller so that CO2 can diffuse in better. That's expensive and it requires energy, so some sort of a life cycle analysis would be needed to see if this approach is net negative. And of course, this is a metaphor or analog to the accelerated weathering approach proposed under geoengineering as well, where you take rocks like olivine, which are fast weathering materials, and you spread it on soils so that exposed area, surface to volume ratio, increases tremendously and weathering rates go up and can draw down CO2 by a natural way. Of course, again, you have to worry about how much energy needs to be used for grinding up and transporting rocks, and whether they can be the places where they can efficiently be used to increase weathering rates. Recycle steel. Steel can be efficiently recycled using an electric arc furnace. So coal versus electric arc for creating coke and other steps in limestone used for cement can save a lot of energy. 1/4 of steel production today is based on recycled scrap. Globally, recycled production is expected to double by 2050, reducing emissions by 20 to 25% from today, which again depends on the electricity production. So carbon intensity of the energy has to be reduced tremendously for these things to work properly. Subsidized changes. Full decarbonization with carbon capture and sequestration is expected to double the cost of Portland cement, a kind of cement that is most commonly used and manufactured, of course. Now about $100 per ton in terms of this full decarbonization. Cement subsidies would need to match that, otherwise consumers will end up paying for it. Zero emission steel is expected to cost 20 to 40% more than standard steel, which is typically about $600 per ton. So steel subsidies would need to reach up to $240 per ton to make them marketable, economic for people who want to use it. For the European Union, we estimate that the cost would be up to 200 billion over 10 years. So ultimately, we have to remember China and India are going gangbusters on building sites, infrastructure and skyscrapers. They use up a lot of cement and steel, and they manufacture a lot of it as well. So developing countries where most construction is happening need technologies to be shared. This is an issue for all aspects of climate solutions. Here is a limestone quarry being shown. Limestone is the source of most of the carbon dioxide emissions from cement production. The other part that has to be considered under cement and steel towards net zero is decarbonization of a skyscraper itself. It takes around 5,400 tons of cement and 1,400 tons of steel to construct a 30-story high-rise building that is about 100 meters tall. Producing these materials releases 5,830 tons of carbon dioxide, 5,830 tons of carbon dioxide that can be brought to below zero by 4 steps: using fewer materials, switching production processes, using low carbon heat sources, and carbon capture and storage. Okay? Looking at CO2 emissions, then business as usual, as we said, is taking up 5,431 tons of cement and 1,429 tons of steel, emitting 5,830 tons of CO2, which then can be reduced by 31% by improving design and using fewer materials. Can be further reduced by another 33% by switching processes involved, which are being considered, practiced, implemented, a matter of making it standard. Decarbonizing heating takes down 6.6%, and capture and storage then would have to take up the remaining 43% to get to zero. Okay, so all are great suggestions, and of course implementation, life cycle analysis and so on are needed, but there is the story of net zero for cement, carbon and infrastructure like skyscrapers. Okay, so let's leave this here and look at other aspects of net zero in a podcast that focuses on other aspects.